Good afternoon and welcome to this session on basics of laser remote sensing. Uh, Laser remote sensing is a technique which enables us to take 3D measurements, that is, to take measurements of X, Y, and Z coordinates by using a laser sensor in conjunction with an aerial camera, a GPS, and the IMU unit. These sensors in conjunction and calibrated together help us to automatically capture uh, the height parameter of the surface that we are sensing. We will look into the basic concept of the system. What are the components of the system? What contribute, what parameters may contribute to errors, and how we can control them and remove some of them, and what are the applications for which this technique would be useful. So the methods for taking measurements of the Z coordinate or the height parameter can be image-based techniques using passive sensors, like for to do photogrammetry, which we have discussed in earlier sessions. These photogrammetric applications can be done through sensors based on a satellite platform or on an aerial platform, or they could be mounted on terrestrial platforms. So satellite-based platforms will have sensors which are so designed that they will take overlapping pictures or images of the same area from two different locations, and then we will use that with mathematical processing to be able to convert the points that we see on the image or the locations that we see on the image. Their image coordinates can be transformed into actual ground coordinates doing a set of mathematical procedures. Similarly, we have sensors mounted on an aerial platform, which could either be an aircraft or a UAV, which would be a close range aerial system. We could also have these kind of cameras mounted on terrestrial platforms, meaning they could be handheld cameras, they could be cameras on our mobile phones, they could be cameras mounted on a tripod stand, and uh, ensuring that we have overlapping coverage of the area, at least from two different locations or angles, thereby covering the object of interest or the study area from at least two different locations. Now, once this processing, mathematical processing that I was mentioning is completed, we will get a set of dense or sparse points. Each point will be associated with its X, Y, and Z coordinate. This technique, which is image-based technique, is more economical than the others, as we will see, but you need an experienced uh, person to be able to, or a manpower to be able to uh, carry out the entire process effectively so that precise measurements are possible. These are called image-based techniques because we rely on overlapping images or photographs taken in a certain way, that is ensuring overlap, then carrying out the mathematical procedure to convert points that we see on the image or points that we can locate on the image into their corresponding ground coordinates. Then we have range-based techniques. Range-based techniques are those in which a signal is sent towards the feature or object that is to be studied or measured. The beam strikes that object and we get a return beam which is sensed back at the from where it was sent, the sensor. So we send a pulse, it strikes the object, and it returns. So the return signal is also measured. Now the time, this range, the two-way travel time is measured, and it is converted into distance by using the relationship between speed of light, distance, and time. So we convert the range into distance. Laser scanners or the LIDAR technology falls into this category. There are other sensors, other active sensors like the SAR sensor, that is the microwave sensors, which are also range-based sensors or range-based technique. However, again, these could be space-borne, aerial, or terrestrial platforms. There are space-borne laser sensors. Aerial sensors can be mounted on aircrafts or UAVs, as in the previous case of image-based sensors. And they can also be mounted on terrestrial platforms, and then they're called terrestrial laser scanners. From these kind of sensors, we get, in comparison to the image-based techniques, we get a much denser 3D point cloud. When I say 3D point cloud, it means that the Z coordinate is also measured. So we again have for each point, we have X, Y, and Z measured. It is a quick and easy but expensive methodology or technique. The instruments that are involved are more expensive as compared to the image-based techniques. It is able to give us the 3D point clouds, as we call them, that is the X, Y, and Z coordinates over a larger area, much quicker than the first method. The cost involved is also comparatively much higher. So the economics of the two is, for the range-based techniques, is much higher. Then the third method would be the manual surveying methods, that is either with the total station or with the GPS, or we can get coordinates from topo maps, which of course the maps have also been surveyed. Now these are points that we get from here, or the resolution that we get for the elevation model is much sparser and of low density and resolution. And it is, of course, because it's a physical process, it is more time consuming than the first two methods. Okay? Then using all these, we can also use procedural modeling or computer graphics to generate 3D models. So today we will be focusing on the range-based techniques of LIDAR, altimetry, or laser scanners, and see how this technique enables us to measure and use 3D data, X, Y, and Z coordinates for various applications. Now, LIDAR is an acronym, and the full form of this acronym is Light Detection and Ranging. So light detection and ranging. It is a laser-based remote sensing technology. Here, we point a small laser at a surface and measure the time it takes for the laser to return to its source. It is an active remote sensing technique, active because the platform itself carries its own source of energy. Yes, the laser energy is carried on the platform itself, and we are not dependent on an external source to provide the energy. Now, and this gives us precise information about the target or the terrain. So the sensor sends the pulse, it interacts with the targets and returns to the sensor. The advantages are, since it's an active sensor, it can be carried out during day or night. One can compare the intensity of the energy that is sent and that which is received. It enables us to map through vegetation, which is not possible in the image-based techniques. Since the optical wavelengths are used, they don't penetrate into vegetation canopy. So creating an elevation model of the terrain beneath the dense vegetation canopy is a limitation in that technique, and LIDAR emerged as a solution to this limitation or drawback of the image-based techniques, to be able to make mapping possible through dense vegetation canopies, also in areas of low contrast or where there is dark shadow. Right? So in case of a shadow situation or low contrast, and especially through dense vegetation canopy. So the laser pulse is a very minute point source, and it is able to penetrate through the leaves or the dense canopy and give us at least a few, even if it is a very, very dense vegetation canopy, the laser pulses are able to strike through in between the dense vegetation canopy, the trees and the branches, etc., and reach the terrain and give us a return, which we are able to measure at the sensor. So the ultimate aim of this method or technology is to be able to produce digital elevation models, DEM, or a digital terrain model for 3D mapping and modeling applications. So any application which requires a very high resolution elevation information or a digital elevation model, as we call it, because we are modeling the surface of the earth or the feature of interest in terms of its elevation or the terrain information that we are able to capture through this technique and use it for different kinds of applications. So the laser scanner is an active sensor, as we've seen, unlike passive sensors, which require, like images and photographs, which require either the sun's electromagnetic radiation or an external source. The mode of acquisition here, now please remember, I will, in the coming slides, I will show you a few data sets of laser sensors, the data that we get through LIDAR technology is non-imaging. It is not a photograph, it is point data, range data, right? And the end product that we, after processing, the end product that we are able to get for it is for identification of features based on their geometrical characteristics. So we are very clearly able to see the shapes, sizes, etc. of different objects and get an idea about their height. So height is obtained at a higher resolution with the dense point cloud. So also these laser sensors are able to give us multiple returns. So when we send the pulse, we can get back the return, get the return at from various locations or at various time stamps. So it could range from the first returned pulse to the last returned pulse, and we could also have sensors which are able to measure the pulses from in between. So we could have a sensor which is enabled to measure multiple returns of the pulse that is sent. This will give us an idea of the shape of the object, and we will be able to distinguish between multiple objects from that pulse, the laser pulse, which will give us a vertical profile of the scene. So it is usually discrete data, but as I said, we can also have full waveform data, that is the entire signal or multiple returns from the signal can be sensed and recorded. It gives us precise details in terms of X, Y, and Z coordinates about the scene that we are looking at, or the object or area on the surface of the earth, or the object of interest. As I said, it gives us a vertical profile of the scene. It is able to penetrate into water through water and vegetation canopy, and multiple returns are possible. Now, let us see which platforms we can use to mount the sensor. Platforms can be ground-based, So we have terrestrial laser scanners, which can be mounted on tripods like this one, and they have associated systems like the GPS, the camera, and the laser scanner. They can be operated in a static or mobile mode. So I can do a stop and go. I can put my sensor at a location, take measurements, move to the next location, or I could mount it on a mobile platform and continuously record data. Then the platform could be airborne, which could in turn be a manned system, that is like an aircraft, which has a pilot and operated by a human being. Or it could be an unmanned vehicle. So we will be able to use UAVs for mounting these LIDAR sensors, like this one. We could also we have several spaceborne area LIDAR sensor systems. The ISAT satellite, which has the glass sensor. Then we have several others, like the Calypso and the LITE experiment. Then we also have planetary LIDARs, LLRI, which is the sensor which is mounted on the Chandrayaan-1 mission, gave us laser data, LIDAR data. We also have other sensors from on other planetary missions from other countries, on the Mars sensing systems and on the lunar sensing systems as well. Now, the operating principle of the laser or the LIDAR system is that, as I said, it is a laser ranging and detection device similar to radar. It uses a laser instead of a radio wave or a microwave, as is done in the radar or the SAR systems. The laser pulse is emitted from the sensor. One makes a record of the backscattered signal, that is, you catch the reflected laser back at to the LIDAR pulse source with sensors. So you send a pulse, it strikes the object, interacts, and comes back. So you emit a pulse and you receive a pulse, right? So there's an emission and there is a reception. So depending upon what feature, is it vegetation or water or built up areas, right? And which wavelength laser is used, we get a return pulse. We have a timestamp and we get the amplitude. We are also able to measure multiple echoes or multiple returns. Now, with this range measurement that we get, we can do a distance measurement with the simple formula of speed of light into time taken divided by 2, because it's a two-way travel. Then we retrieve the plane position and the altitude, and the computation of the precise echo position is carried out. This process is repeated millions of times by the laser instrument because it sends a very high frequency pulse. Laser instruments emit a very high frequency pulse. So there are millions of points that we get in a very small area. So by repeating this process several times, millions of times, the laser instrument, and it produces a dense map of the surveyed area. We call this, the term used to describe this is a 3D point cloud. Right? So what's happening is this pulse is sent. It strikes back to the sensor. Hello? It is sensed back at the sensor, and the time taken is noted. So a timestamp is attached to each return. And we use this relationship to calculate the distance. So you have a transmitter, and you have a receiver, right? It is received, the transmitted pulse, and the received pulse, the time of travel is measured along with the amplitude. Now, when we mount it on an aerial platform, this is how pulses are sent. It strikes various objects that it encounters. Therefore, millions of very precise laser measurements are made from a precisely located aircraft. Measurements are taken with the help of a GPS, right? And we get a detailed and accurate 3D map of the surface or the Earth surface that we are sensing, and we call it a point cloud. So the components that comprise of the laser system or the LIDAR system, there are 3 such components which we need to integrate into either satellite-based platforms or aircrafts or automobiles for a mobile mapping system, or on drones or UAVs. So the first sensor is the laser scanner. So the LIDAR system pulses a laser light from various mobile systems through air and vegetation, and even water. For bathymetric LIDARs, we will see that the scanner is receiving the light back, that is the echoes. We call these echoes, measuring distances and angles. The scanning speed is influencing the number of points and echoes that are measured by the LIDAR system. And the choice of optics and the scanner influence the resolution and the range in which we can operate the LIDAR system. Then we have navigation and positioning systems. For absolute position and orientation. These provide us the absolute position and orientation. Now, it is crucial to ensure that the data are in usable format. For this, we use the GNSS, or the Global Navigation Satellite System, for accurate geographical information regarding the position of the sensor. So it gives us latitude, longitude, and height. Then we have an inertial measurement unit, that is an IMU, which defines that at this XYZ location, or at this longitude, latitude, and height, the precise orientation of the sensor is provided in terms of roll, pitch, and yaw. Right? So orientation and position are provided with these 2 sensors. The data recorded by these 2 devices are then used to generate or convert data into static points, and this forms the basis of the 3D mapping point cloud. So the laser sensor sends a pulse with which we are able to measure the distance. The absolute position and orientation is provided by the GNSS and the IMU. And in addition, we may also have in some systems, we may also have cameras attached, so that we get, at the same time, we are able to get an image. Then the computing technology is based on the fact that we define precise echo position. This is required for onboard data visualization and post-processing, and it also increases precision and accuracy in the 3D point cloud. So this is how on the aircraft, the example is given for an aircraft, the same systems is followed for the other platforms as well. So we have this is the ground which is being sensed, right? Pulses are sent and received. We have a DGPS system, a differential GPS system, an INS, and the laser sending device. So this is how those precise measurements are taken with these basic components, carefully calibrated very precisely with each other. Right? So what are the parameters that we are able to measure during laser scanning? So if we know the X, Y, and Z, that is the location, then we know the orientation, that is the roll, pitch, and yaw, that is the angle. We are able to calculate the range because we also know the time. We have the angular measurements. We can now derive the X, Y, and Z position of this point on the ground. Okay. So to give you a summary, we can see the laser components and how we do the calculation. So you have a laser scanner, we have a GNSS receiver and a reference station because we are doing a DGPS measurements, and we have an inertial measurement unit, IMU, to be able to measure roll, pitch, and yaw for orientation. So the laser emitter, receiver, the IMS and INS, IMU and INS units, the recorders, and the storage devices, with which we get the time of pulse sent, the time of pulse received, the angle of scanning, and the position of the scanner. So what we have here is the laser scanning system, which consists of the rotating mirror and the laser sensor. These give us the angle between the laser beam and the nadir, and the distance between the laser and the measured point. Now, for absolute orientation determination, we use the GPS and the INS together. The GPS gives us coordinates of the GPS antenna, of course, in the WGS84 reference system. And the aircraft laser sensor gives us attitude angles, that is the roll, pitch, and yaw, or the roll, pitch, and heading angle. Okay. So with these measurements, we are able to calculate very precise, ultra dense X, Y, and Z coordinates over the study area or over the area of interest. Together with this, as I said, we can have additional sensors mounted and calibrated with the laser scanner for orthophotography. That is, we can have an optical camera to get pictures, so that together with the point cloud, as I mentioned earlier, the data that we acquire through the laser scanner or through LIDAR technology is not image data. It is not a photograph or intensity data. It is range data. It is point data. So we get X, Y, and Z points. Since the data is very high resolution or dense, we get the impression of it being a point cloud. Therefore, it is termed a 3D point cloud because X, Y, and Z coordinates are associated with each measured point. Then we could also mount infrared cameras, right? So any other additional sensor can be mounted to get an image associated with this data, which makes interpretation easier. Now we will quickly go through the concept of multiple returns. So as I said, the number of returns can be measured. So the sensor has to be designed so that it is enabled to measure these multiple returns. So for the first stop from canopy, that is, this is the first returned pulse from the first point that it encountered, the pulse encountered, and it's returned from here. So we assume that this would be from the highest point, that is from the top of the canopy. Then those points which penetrated through the canopy and reached the ground would be the last stop from ground. So the last stop or the last pulse would return from the ground. Now, if we have both these returns, we will easily be able to calculate the height of this object, whether it's a tree or whether it's a building or a tower, right? Now, similarly, we can have multiple returns. The first return, then the second return from a point lower down, the third return, and the last return from the ground. So this is an example of 4 returns, 4 return pulses being measured. Similarly, we can have multiple returns. Space-bound LIDARs and other terrestrial systems are also capable of measuring the full waveform. That is, the entire backscattered signal can be measured and sensed. Now, with these multiple returns, we get an idea about also the not just the timestamp, but also the amplitude and the shape of the curve. These also give us important clues for classification of the data points. Okay. So each laser pulse can produce multiple consecutive measurements from reflections of several surfaces in its path. Now, this like this. So this provides detailed images of vegetation structure and density and returns data from the ground under the tree cover. Now, when we look at this, I think the term images would not be so correct because it's not a photograph, but it gives you a perception of it being an image because they are very dense point clouds. So this is how you will see the collection of points from the ground and from points in between the canopy. So from the top of the canopy, in between the canopy, lower down, and from the ground. So the first return pulses, the second return pulses, and the last return pulses. Right? So the description says that the image on the left, this one, is a point cloud LIDAR point cloud view of the tree in the photograph on the right, and each point is colored by the return colored by whichever return it was from that particular pulse. So the red is the first return, the yellow is the second return, and the green is the third return or the last return, and is most likely to be from the ground. And the first return is most likely to be from the top of the canopy. Okay. Now, to realize accurate and long-range measurements, the laser pulse should have the following characteristics. It should be of high power. It should have high power, short pulse length, high collimation ability, that is directionality, and narrow optical spectrum. It should also ensure eye safety. So laser pulses need to be eye safe to be able to operate on sensors which fly low, like the UAVs or ground sensors. Right? So, and also, as I said, they are very narrow, operate in a very narrow optical spectrum, the laser pulses. Okay. A few terminology that we use is the footprint, that is the area illuminated by the laser pulse, and divergence, which is the angle of deviation from its path. We will not go into detail about how lasers are generated, etc. Right? So it uses either a laser pulse or a continuous wave. Then the properties of the laser, as we discussed here, are high energy. It needs to be able to collimate, that is, it needs to have directionality. It has to be coherent, monochromatic, and all these properties of the laser make the LIDAR data very, very precise. Right? Now, when we start a LIDAR project for measurement, what would be the general specifications and how would we decide them as a user? To decide what kind of laser scanner I need would be dictated by the level of accuracy or precision that is required in the end product, what point density, at what range you need to scan, right? Whether it needs to be from a long range or whether you need to scan from a short range, or what kind of swath, how much area you need to cover into your project requirements, for your project requirements. The GNSS, what are the reference stations, right? Whether it's terrestrial or whether we have a moving receiver. So whether we are using DGPS, and is it compatible? Yes. Do I need to use a ground station or not? Then what kind of battery requirements we need, internal batteries or external batteries. If we need to do data capture for a long time, we might need to use external battery sources, right? Then mounting the laser system, can it be mounted easily on aerial platforms or drones or on an automobile like a car? Yes, how do we mount it? Do we have the required mounts or not? What format is the file that we acquire for the measuring the coordinates, what format is it in, and how do we do post-processing, right? For classification or for visualization or for DTM, that is digital terrain model generation, etc. Right? And how are we going to use the post-process data for what kind of application? Then we come to terrestrial laser scanners. As I said, terrestrial laser scanners are mounted on a ground-based platform like a. Right? So the main features are that it is from short range to long range, and it has very high data acquisition speed. It has a wide field of view and can be controlled while scanning, gives you high accuracy and high precision ranging. It has mounting pads for optional digital cameras and is integrated GPS receiver with antenna. So this is the kind of data that we get from the terrestrial laser scanner, right? This has this statue that you see here gives us an impression that it is an image, a photograph, but it is not a photograph, it is a laser point cloud. And you can appreciate the fact that we are able to see even the very small carvings at very high resolution. So this is the overview, and when you zoom in, you are able to see every small detail on the statue. So if we need to monitor such structures for damages or for changes that have happened, it can be done for small cracks, etc. We can see these easily. You can also see that the very small carvings and small structures are also visible at a very high resolution. Each window, etc. is visible. Then we have certain space-borne laser sensors, LIDAR sensors, on planetary missions, that is on Chandrayaan-1 and on others, as I mentioned. The Calypso LIDAR, which is for specifically for atmospheric studies. The ISAT mission, which is for studying the ice, cloud, and land elevation. Okay. Calypso was launched in 2006, and it is specifically used for atmospheric studies. The ISAT spaceborne LIDAR system was launched in 2003, and it operated in 2017. The main objective was to study the changes in the ice sheets, and as secondary scientific objectives, clouds and aerosols, land elevation, vegetation covers, and sea ice thickness were also studies. It was the first LIDAR used for continuous global observations of the Earth. It emitted, the sensor is glass, geoscience laser altimetric system, and it emitted laser pulses in two wavelengths, the 1064 nanometer and 532 nanometer for surface and cloud tops. The laser footprint was 70 meters, spaced at 172 meters along track, and it enabled ground elevation retrieval, identification of vegetation structures and height estimations. And the main point of interest was that it was a full waveform data. So the entire backscattered signal was recorded, and we were able to do very high precision classification in terms of land use features. The next in continuation of the system is the ISAT-2 Atlas instrument. This was launched in September 2018, and it is meant to provide a 3D portrait or a 3D point cloud of the global surface of over a period of time. And this would also be instrumental in tracking changes in terrain or ground, glaciers, sea levels, forests, clouds, and more. So again, now the measurements are taken at every 70 centimeters, which is a much smaller footprint and gives us denser spatial sampling. Now, with this exact information of the satellite location, time of flight, and the photons that we measure, and the direction of the laser that it is pointing, the distance is measured, calculated, and then it is converted into heights of those points. So it's a photon counting LIDAR. Excuse me. Now, the next point of discussion is the modes in which we acquire data. So the mode of acquisition could be discrete, yes, or it could be waveform. So discrete laser systems, as you see, will give us lesser number of points or returns like this. However, if the sensor is able to give us a full waveform return, it means that the entire return signal is measured. Now, this allows us the capture of small deviations in the shapes of the reflected pulse as compared to the shape of the outbound pulse. So in discrete point LIDAR returns, if we have one point here and another point here, as opposed to the full waveform signal, which gives us the entire signal. So you can see and appreciate the difference between the two. The discrete systems capture only the exact times of the peaks of independently recognizable return pulses, and peak intensity is also measured. Okay. So the waveform, when we look at it, the roughness and slope of terrain can be measured. So you can appreciate the difference here. And different terrain types will have different effect on the waveform, how it interacts, depending upon the slope and the kind of terrain, the roughness and the slope. Now, there are a few case studies that were done. So, footprints of the ISAT-1 laser data and the image data, the waveform processing was done. The waveforms were denoised, decomposed, normalized, and then the footprints were studied for calculating over heights and also classifying land use features using the full waveform data in conjunction with satellite images. So the full waveform spaceborne LIDAR data, the range and amplitude was used for urban land cover classification. Similarly, you see, we can see an entire tree canopy with its exact shape. So height classification was possible. So low vegetation, vegetation with low heights, vegetation with more height, etc. was distinguishable. Also, ground elevation was calculated. Similarly, we can use laser sensors on interplanetary missions like the one on Chandrayaan-1. Right? So it will give us an idea, a 3D profile of lunar craters and the lunar terrain. Very precise measurements can be seen. We are able to see even in the shadowed portions, which optical elevation information from optical sensors will not give us. So this was a case study which was done here. The LLRI on Chandrayaan-1 and LOLA data over the south poles of the moon. This is the lunar surface. You can see the elevation model and the slope map for the lunar south pole. So we are able to see craters and also what is there inside the craters. So you see, each small detail inside these craters is also visible, which was not possible. The small crevices, dips in the crater wall, etc. So all these undulations inside the crater where there is a lot of shadow is also visible in the laser data. This was not possible with only the optical images. Similarly here, this is the profile of the crater. This is the shaded model, and these are the profiles plotted. Now, LIDAR sensors can also be topographic. The airborne sensors can be used for topographic mapping, that is on the ground. We've seen that we need some associated systems, a DGPS and an IMU, and of course the laser sensor, it is scanning. And we can also have bathymetric LIDAR, that is to sense water for water resources studies. So we have an NIR system, NIR laser, which gives us a return from the surface, and a green laser which penetrates the water and goes inside and gives us a return. So we are then able to do analysis for bathymetric purposes. Also, the intensity plots from the laser and from area photographs can be compared. So if it is an infrared laser, if we have an associated camera, then the infrared wavelength or the intensity of the infrared on the image and the intensity of the infrared from the laser scanner can be compared and used for data classification. So as we saw just now, same thing can be done for bathymetric purposes. So sea surface, sea floor, and the water column can be studied by using two returns. For example, from the IR gives us from the surface return, and we get a bottom return from the green laser. So this intensity can be plotted and studied for bathymetric purposes. Then we can use these laser data for very precise height information extraction and improving feature extraction for building detection, as you can see here, and urban feature extraction like roads and modeling buildings in 3 dimensions. So this is one case study in which automatic road extraction using aerial laser scanning and high resolution satellite data was done. The study was able to distinguish between roads and buildings of the same heights, and also among elevated roads and roads on the ground. That is, if there were flyovers, etc., the rule sets made it possible, and the data used in conjunction, that is the laser data and the image data used together with certain rule sets that were devised, enabled distinction between similarly reflecting areas on the image. By the use of height component, we were able to distinguish those. So you can see here, this is filtered data. These are the curves of the flyovers, and the red points correspond to very high buildings. Here you can see the medium rise buildings in the light blue cyan tone. Then there are certain flyovers and low buildings, low height buildings, which are also in the same height range. Then we come to the ground and the near ground data points. Fine. So this is the flyover that corresponds to this curve here. These are the height points. The second flyover corresponds to these cyan points. There are also, as I said, few buildings which have the same height. Okay. So these roads and elevated roads were, we were able to make a distinction between these using both laser data and intensity data from images together. Okay. Now the advantages of laser technology are that it gives us very high accuracy in the range of centimeters and also millimeters if we talk in that range of terrestrial laser scanners. It enables fast acquisition and processing. So we can acquire data over large areas in very little time. The digital elevation model can be generated also very quickly as compared to the image-based techniques. Also, there is minimum human dependence. So most of the processes are automated. Then there is little, because it's an active sensor, the weather and light dependence is not there. So data is collected independent of sun inclination and can also be done during bad weather conditions or in shadowy conditions or at night. Then it enables the biggest advantage being the laser being able to penetrate through canopy, vegetation canopy, right? So laser pulses can reach beneath the canopy and therefore enabling us to generate measurements of points. This is not possible through image-based techniques like photogrammetry. So satellite photogrammetry or aerial photogrammetry, wherein we use optical cameras, operating in the optical ranges of the wavelength, would not give us the capability of being able to see beneath dense vegetation canopy. This is the biggest advantage of LIDAR technology. Then it gives us data at very high density. So higher data density, multiple returns collected in 3 dimensions, independence of GCPs. So only very few GCPs are needed to keep reference receiver for the purpose of the differential GPS processing. Otherwise, there is no need of GCPs. This makes LIDAR ideal for mapping inaccessible and featureless areas like deserts, etc., or over vegetation canopy. We can also acquire additional data like images if we have an attached camera system. When we come to the economics of the system, it has been found that by studying comparative areas and comparative analysis, that the LIDAR data comes out to be more economical in several applications. This is because when we consider speed, accuracy, and density of data. Right? However, accuracy is affected by, there is difficulty in locating ground control points corresponding to LIDAR coordinates because it is point data and not image data. The vertical accuracy is determined by comparing the Z coordinates of the data with the true elevations of a reference, which is generally a flat surface, and accuracy is stated as RMSE. And we know the relationship of calculating the RMSE value. Right? So the errors for a typical sensor range, the range accuracy is in the threshold of 1 to 5 centimeters. The GPS accuracy ranges from 2 to 5 centimeters. Scan angle measurement accuracy is about 0.01. The INS accuracy also very, very precise. Right? However, when we come to the final calculations, the final vertical and horizontal accuracies that we achieve are in the order of 5 to 15 centimeters and 15 to 50 centimeters at 1 sigma. So for vertical and horizontal accuracies, we range the order of 5 to 15 centimeter and 15 to 15 centimeters is achievable, which is very, very precise measurement. So the sources of errors here could be due to the error due to sensor position, which could be due to errors in GPS, INS, and the GPS-INS integration. Errors could also be due to angles of laser travel, as the instrument may not be perfectly aligned with the aircraft roll, pitch, and yaw axis. So there may be differential shaking of the laser scanner and the INS, okay, due to which the measurement of the scanner angle may have an error. The vector from the GPS antenna to the instrument in the INS reference system is also required in the geolocation process. And if this vector is observed physically, we may have an error in its observation. Okay. Also, there may be errors due to complexity in the object space. Right? More sloping surfaces would lead to more uncertainty in X and Y coordinates. The divergence of the laser pulse in a finite diameter footprint instead of a single point on the ground would also lead to some uncertainty in the coordinate measurements. And there could be multipath errors due to the laser pulse. Okay? Multipath error. Multiple reflections. Then we come to the last section, that is the applications for which this technology can be used. It can be used for urban modeling, right? So 3D models from bare earth and reflective surfaces can be used for analysis and visualizations for urban planning and other urban applications. We can also have corridor applications. So we can map a river corridor or a road corridor, etc. Right? A railway corridor or a highway corridor to provide very accurate data for highway design. In case of the railways, it will support engineering design, and these can be used for, to track data required for train control, controlling the trains that are plying. We can also have a corridor for the power line monitoring and management. So the section of high tension lines can be monitored. Sorry. Right? So you see, we are able to get very precise data about the sag of the wires and between the sections, etc. So that proper transmission of electricity can be done through these wires. Then whether vegetation is affecting the power lines, etc., or whether there is some encroachment, etc., can also be monitored. Then, of course, as we saw, 3D city models of very precise measurements are possible. So if you see here, the digital surface model is of the order of 1 meter. It's a raster data. So it is of the order of 1 meter. That means at every 1 meter, we have a point sampled. Similarly, we see this. This is the zoomed portion. So we can use these points. These are not images, only laser point clouds. And these can be used for city planning, city monitoring, 3D city modeling applications, and any other applications for which urban monitoring or planning is required. Then, as I said, we can also use them for bathymetric applications, landslide monitoring, cellular network planning, water resources applications, that is for calculation of several hydraulic parameters like river width, surface level. The DTM of the catchment area can help us do planning, calculate the discharge, look at the depth of the water body with bathymetric LIDAR, and of course, forest mapping. So the data points that will be available under the canopy of a tree can easily be analyzed, and the laser pulse passes through as the laser pulse pass through the small gaps in the forest canopy. Then river estuaries can be measured. Now here, because there is very little change in the elevation, so we need a very high resolution system to be able to measure the small changes that can be seen. So laser systems are very accurate systems which are also able to measure small changes, and these enable us to do these kind of measurements. So with this, we come to the end of this session. We will take a 5-minute break and then we will come back for the interactive session. Thank you.